All right. I've been getting a few questions about a particular kind of question, a calculation problem that we have in the practice quizzes. And because calculations are part of quiz 3, which we just did, and quiz 4, like some of the upcoming stuff, I want to give a general sort of, I want to talk through how to approach this kind of question. Obviously, the simple waves, that's done with quiz 3, but as we move forward into other things, it's going to come up again. And similar approaches, even though we're doing different types of calculations, similar approaches will be relevant. So here is a new wave illustration that I generated for this video. This is, you should be, if you've tried the practice quiz or the practice calculation quiz, this should be familiar to you. You see the waveform, I've got the 0 line, that's the equilibrium point marked out, and I've got the beginnings and ends very carefully marked out so you can see exactly when this point is, what the time is for this point, and what the amplitude is there and there at the peak and the trough. Okay, so we have a clearly defined wave, and there's various things that you could be asked about this. The one that I've been getting questions about, so this is what I'm going to approach, is what is the frequency of this wave? So again, we look at this wave, and what we can see, we can see a number of repetitions in a particular amount of time. Now, we have our formula sheet here. If we're asked for the frequency, the main formula we're looking at is this one where frequency is defined in terms of the period. Now the period, of course, is the time it takes to do one cycle, but what we have here is 3 cycles. So I'm going to give you 3 different ways to approach this. And they all use that basic knowledge and sort of carry it forward in different directions. So which one makes the most sense to you? It'll depend on the individual. They are all mathematically valid. There's slightly different things to watch out for in each of them. So the first one is to first figure out what the period of the wave is. Right? We have 3 cycles there. So what time does it take to get 1 cycle, and then plug that into our formula and we'll have the answer. So here we have 3 cycles. And we start at 0 and we go to 0.005. So if I want to figure out what 1 cycle is, I can say 0.005, this is coming out really small, sorry about that, divided by 3, and my calculator gives me 0.00166666667. Okay, and that 7 is really just, it's given up giving me extra 6s, and it's just showing me, it's just rounding the last one off. Now I'm going to see if I can increase the size of this. That's not right. Not easily. Okay, so you'll have to play along yourself, or I will tell you the answers that I get. Now, the thing to watch out for here is it's really tempting to start rounding right away because then we have less to input into our formula. But when you're doing calculations, when you're doing a string of calculations based on some measurement, the universal rule of thumb is if you have to manually type it in, don't round anything off until the very end. Okay, if you start rounding stuff early, then you get a little bit of an error, and every step that error can get compounded. And I'll walk through how that, we'll see that happen here. So here I get, the calculator is giving me 5 6s before the 7. So it's 0.001666667. And I know mathematically it would be, if I let it give me 20 digits, they'd all be 6s until the 7. But anyway, we'll go with that. Now, if I were to round this off to the nearest millisecond, I would say it's 2 milliseconds. That's a really bad idea. I just told you don't round off. But just for illustration, if I take 2 milliseconds, 0.002, plug that into my formula for frequency, frequency equals 1 divided by the period, and if I want 0.002, that would give me exactly 500 hertz. If I round it off that. I'm not going to round it off that way because I know that's going to be wrong, but just to illustrate how bad of an idea that is, if instead I put in exactly what I got here, and I can click on that and it gives me the exact number. Now, I don't know if you can see this. I had 500. When I plug in the exact number that the first calculation gave me, it says it's 599.99988, which is just the tiniest hair below 600 hertz. And if now that I've finished that, that is my formula. Now I can round it off. So 599.99988. So there's, okay. I am going to round that off to 600 hertz because, let's see, that's at least hundred thousandths of a second, or what would that be? Maybe 10,000ths of a second. Or it's around it there, it'd be 599.9999. That is way more precision. We are not dealing with those tiny amounts of hertz. With frequency, you can generally, for speech anyway, round it off to the nearest hertz and you're totally fine. Okay, so that's one approach, and we got to 600 hertz with a bit of rounding right at the end. Now, another approach, I'm going to come back to this image. Another approach is to say, well, what if this was just one cycle? We know it's not. We'll deal with that at the end. This is the thing. We've got to watch out for what assumptions we're making and what things we need to adjust. If this was just one cycle in 5 milliseconds, then I could calculate that. That's easy enough. 1 divided by 0.005, and that says 200. Well, I know this isn't a 200 hertz, but a 200 hertz wave would have one cycle in that window. We have 3 cycles in the same amount of time, and what that means about frequency is the wave we have has 3 times the frequency of that wave we just calculated. That wave was 200, so 200 times 3 is 600 hertz. So that's another way to get there. Mathematically, it works out exactly the same, but we've kind of come at it in a slightly different direction. And notice that because the numbers were kind of nice and whole numbers, nothing fractiony there, we didn't have to do any rounding at all, even though we're doing precise calculations. Okay, so one approach, we find the period for a single repetition and use our formula straight up. This way, we use this period for multiple repetitions, find that frequency, and then do some reasoning from that to the frequency of the wave we actually have. And the third way is to use a slightly adapted formula. And this is absolutely valid. It is definitely going to be more comfortable for people who have more of an intuitive sense of what's behind the formulas. Some people, their mathematical reasoning works that way. Some people don't. Like I said, some of these approaches will be more amenable to some people and others to other people. So what I would say here is our formula is, I can call that up for us. Our formula, which we have over here, frequency equals 1 divided by period. So the frequency equals 1 divided by the amount of time it takes to do one cycle. We can actually adapt this, and I don't have it written up, but the frequency equals, if you have n cycles, like any arbitrary number of cycles, the frequency is n divided by the time it takes to go through that many cycles. Okay, what does that mean? What does that mean? That's a good question. Let me make that make sense here. Sorry, my illustration just disappeared. Okay, we will get there. Okay. Oh, I gotta make that bigger again. There we are. Okay. So we've got this wave here. Now there are 3 cycles. We know that because it starts at the top. We go through a cycle. We end up where we started. That's 1, 2, 3 cycles. in 0.005 seconds. So if I, that's not what I'm after. Clear. So if I say 3 divided by 0.005, it tells me 600. Isn't that nice? That's actually, those who are more, like, that's mathematically very, very close to the previous one. But it is a slightly different approach. And it gets us to the same place. It still gets us to 600 hertz. One of the glorious things about math is there can be multiple ways to solve a problem, and as long as each of them is valid, they will each get you to the same answer. There are some exceptions when you're doing calculus that we don't have to worry about because we're not doing calculus in this course. The Fourier transform we're going to talk about, and that involves some amazing calculus, but we're not doing it. The computer's doing it for us, so don't worry about it. Okay, so just to recap, this is a long enough video already, but we've covered 3 distinct mathematical approaches to this kind of problem. You can figure out the period for a single repetition, even though you're given multiple repetitions, and then plug that straight into the formula as we have it on our formula sheet. You can figure out the frequency for if the whole window was 1 cycle, and then convert at the end based on how many cycles there actually are, and your understanding of how frequency works with that. Or you can use this slightly adapted formula, F equals N divided by, you could call it T sub N. So N, the number of cycles, divided by the period, the amount of time it takes to complete that many cycles. Each of these approaches is valid. With each of them, let's see, the first 2 actually involve multiple steps. So if you have any rounding at all, remember, only do the rounding after you're finished the last step. Don't do rounding after the first step and before you plug into the second step, because that is where a lot of people go off the rails and you end up with an answer that is much further away from the precise answer than what is appropriate. So don't round too early. Ever in any mathematical or scientific measurement or series of calculations, don't round too early. That's the main issue to watch out for with number 1. With number 2, you have to keep in mind that reasoning, right? We said, okay, if the full, what was it? It was the full 5 milliseconds was a single cycle, then our frequency is 200 hertz, but we have 3 cycles, so we're going to multiply. We know that this wave is 3 times the frequency of one that would only have 1 cycle in that window. So it's 3 times that. 200 times 3 is 600. And the third way was to adapt our formula to that N divided by T sub N, which again, I think that's probably the nerdiest one, mathematically speaking. Some of us are nerds of that order and would be happy with that, but many of us aren't, and that's totally fine because you have 2 other completely valid ways to get there. Yeah, calculating on simple waves isn't something we're going to be doing in the next quiz and the further on stuff, but we're going to be doing some stuff like resonance, and it's going to be on the order of, hey, here's some numbers divided by some other numbers that gives us a result, and we may have to do it in multiple steps depending on various things that we'll come across as we go there. So something analogous to these different approaches may be available to us there. Big rule, like even if you just follow the formulas straight as they are on the formula sheet, only round at the very end, and that should keep you safe on that side. It is good to know, to understand how the values relate to the thing in the real world. That's how we get that, hey, what if this was just 1 cycle, and then we do that reasoning further based on how many cycles there actually are in this window. That has to do with a sort of more comfortable understanding, I think, of how the numbers that we're playing with on one hand relate to the actual physical things that we're dealing with in the world, and the graphing, the sort of visualizations that we're dealing with on the page there. So yeah, anyway, approach it however is most comfortable, least daunting to you. And as always, reach out to me if you have questions. That's all for this video.